Hello there, and welcome to our presentation on patterns of behavior for solutions of certain discrete Riccati equations derived using the timescale calculus. My name is Ted Mogentin, and I'm here with my research partner, Karen Schmidt. And then this project was also conducted with the faculty guidance of Professor Chris Ahrendt. We are here recording for the April 27th, 2020 CERCA. This presentation is being recorded on April 17th. So to begin, we're going to go over what is the Riccati equation. So in the real numbers, the self-adjoint linear equation is defined as px prime prime plus qx is equal to 0. Now, this equation is able to be transferred into px prime prime plus p prime x prime plus qx is equal to 0 using chain rule. Then, transforming the equation into a nonlinear form, we get z is equal to px prime over x. And then finally, if we were to take z prime ends up simplifying down to negative q minus z squared over p. And this value, this equation here for z prime is what we define to be the Riccati equation in R. So now that we understand what the Riccati equation is, we are now going to ask, what is a timescale? A timescale is denoted with the boldface t and is any non-empty closed subset of R. So, for example, we could have the entire real numbers is the most common timescale that most of us are used to working with, and that is in which differential equations is based in. For those of you who have heard or worked with difference equations, that is another example of a timescale in which t is equal to z. And then other examples would be the Cantor set or any other h times z, but it can be any set that is a subset of R. So before we continue, we want to go through a couple of definitions for the timescale. The first being the forward jump operator, which is denoted with a lowercase sigma. And that is defined to be the infimum of the value, which is basically saying that it's the next point in our timescale. And in the case that our timescale is the real numbers, then there is no next point because all of our points are infinitely close together. The graininess operator, denoted by the lowercase mu, is defined to be the forward jump operator minus t. So basically this is just saying how close are all the points together. If we have a very small mu, then we are approaching the timescale with where it's just the real numbers, where everything is infinitely close. If we have a very large mu, then everything is spread out. And the final definition that we have is given a function f of t from the timescale to the real numbers, f of t is said to be delta differentiable, denoted with superscript capital delta in t, provided case 1 where mu is equal to 0, then it's just our generic limit definition that we are used to, or in case 2, when mu is greater than 0, then it is defined to be f of sigma of t minus f of t over mu of t. So here's a quick summary slide of differential equations and difference equations as far as what we might be already used to. I'm not going to go over this slide, but I encourage you to pause the video to go through some of this vital information. What is interesting is when we just consider the general timescale case, when t is just any value of t. And so what we have here is we have a delta differentiable function saying that it is delta differentiable if and only if that limit there exists, f of sigma of t minus f of t over sigma of t naught minus t. And this leads us to the self-adjoint linear equation defined with the delta derivative instead of the normal derivative that we're all used to. So, given that, we now are going to take that delta derivative of the self-adjoint linear equation, and we're going to end up doing the same thing that we did in the beginning, where we take the z substitution, and we then end up making the quotient, using the quotient rule and algebraic simplification to come up with the delta derivative of z. And this gives us our discrete Riccati equation. And we can also put that in a recursive form with the z sigma equal to pz minus pq mu over p plus z mu if we wanted to as well. So to simplify now, we are going to try and get rid of the parameter mu just because of the fact that dealing with one less parameter will make things easier down the road. So by replacing q with q mu and p with mu over p, we end up with z sigma is equal to z minus q over 1 plus zp. And then, of course, you can also think of that as a sequence form as well. Zn plus 1 is equal to zn minus q over 1 plus znp.
Okay, so at this point, in order to look at some equilibrium solutions and some periodic solutions, we're going to assume that P and Q are constants, and we're going to do that for the rest of the presentation. And so to look for equilibrium solutions, we're going to set Z naught equal to Z1, or in terms of the Riccati equation, we're going to say that every Zn plus 1 is the same as every Zn. And after a little bit of simplification with that equation, we get down to the initial condition Z naught is equal to either plus or minus the square root of negative Q over P, and that's going to be our two options for equilibriums. And so this is just a little illustration of those two equilibriums. So given the P and Q values, the square root of 8 divided by 2 is going to be the square root of 4, which is plus or minus 2. And so we have those two positive and negative equilibriums. So there is one special case in which PQ equals -1, and we rearrange that so that we can replace P with -1 over Q. And then when we plug that into the Riccati equation, we get down to Z sigma, that is every Z value is going to be equal to -Q. And so regardless of whatever Z value you plug in for that initial condition, it will jump down to that equilibrium at the -Q value, which in this case is -1. Okay, so again, there are two equilibrium solutions at Z naught equals plus or minus the square root of -Q over P. And so we have a theorem that we found based on that. So if both PQ and P are less than 0, then for all initial conditions Z naught, the Riccati equation is going to converge to that negative equilibrium. And if PQ is less than 0, but P is greater than 0, then all initial conditions are going to converge to that positive equilibrium. So here we have an example of converging to the negative equilibrium. We call it the converging equilibrium, but it's really an asymptotically stable equilibrium, and then the diverging equilibrium is what we call an unstable equilibrium. But as we see, the PQ is, of course, negative in value, and then the P is also negative in value. So the Riccati, or the solution is going to converge to that negative equilibrium. We also have non-oscillating solutions in which the P value is again negative, PQ is also negative, so it's still going to converge to that negative equilibrium. Some graphs can also exhibit both converging and diverging oscillation. That is, it diverges from the diverging equilibrium. In this case, that's the negative equilibrium. And then at a certain point, it sort of breaks, and then it jumps up to the positive equilibrium, and it converges from there.
So the previous examples took place when PQ was less than 0, and it showed converging behavior. We're now going to see examples of how when PQ is greater than 0, it could lead to periodic behavior. So going back to our original Z sigma equation, recall that if Z is equal to -1 over P, then we have a 0 in the denominator and thus an undefined value. So what we end up doing is defining un to be the value of Z naught such that Zn plus 1 is undefined. Thus, that means that -1 over P is Z naught. And if you were to algebraically solve, you could end up finding any U value. And for instance, U1 would be 1 minus PQ over -2P. Now, you could continue to algebraically solve these equations, but eventually it gets pretty heavy. So we ended up finding a pattern, and to do that we have to define a variable x. So we assume that tangent squared of x is equal to pq. Then uk is equal to negative tangent of x over p times tangent of kx plus x. And because we have a periodic nature within the tangent of x, this ends up leading us to a very important idea. And that is that if we have tangent of x squared of pi over k equal to pq, then for any k greater than 2 existing in the natural numbers, u of ak plus c is equal to uc. This is basically just saying that the u values are periodic. But it doesn't stop there. The u values are not the only things that are periodic. Actually, the entire equation is periodic. And this leads us to a very important theorem. For all values of z naught, the Riccati equation will be periodic with period k if and only if pq is equal to tangent squared of pi over k. And again, k is a positive natural number that is greater than 2. So just a quick example of this. Here we're going to let k be equal to 3. And we notice that we have a periodic solution of period 3. And all the values are either going to be at that initial condition of 4 or the other two values that you see bouncing up and down there. Here we have a second example in which k is equal to 5, and here we have two z0 values, z0 being equal to 4 and z0 being equal to negative 1. And this just shows that it's independent of the z0 value. It's going to be periodic regardless. The final example, we have pq being equal to tangent squared of pi over 7 plus an additional 3. And what we see here is that because of the fact that no value of k will get us to that tangent squared of pi over k is equal to pq, because we have that extra 3 there. And because no value will ever get us there, this situation is never going to be periodic no matter how far out we go. And this graph kind of shows that. What we have done here today is we have derived the discrete version of the Riccati equation, and we have accounted for every possibility of that equation. A review of what we have shown is here on this slide. We thank you for watching our presentation. The support from this project came from the Student Below Commitment Differential Tuition Funds through the University of Wisconsin-Eau Claire. Thank you for listening. If you have any questions or comments, we'd be happy to address them below. Have a great rest of your day.